In this video, we're going to begin discussing the uncertainty of the numbers used in our calculations. And in order to do this, we're going to look at a real-world example of space travel. Several years ago, India launched its Mars orbiter spacecraft to travel to Mars, orbit the planet, and make measurements of the contents of the atmosphere, which it's currently doing today as we record this video. The spacecraft weighs around 3,000 pounds in total. It's going to travel around 485 million miles in total. And most importantly, for this conversation, researchers calculate that it will use roughly 200 tons of fuel on this journey. So, my question for you is, if you were planning this trip, how much fuel would you actually pack on the spacecraft? Would you provide exactly 200 tons down to the ounce? Would you add a little bit extra just in case? And the answer to this question really depends on how accurately we know values like 200 tons of fuel. And the ways in which we write out numbers communicate information about how precise those numbers are. When we write out large numbers, zeros are often used as placeholders to show the order of magnitude. So when we write out this 200 value, we don't actually know whether or not the zeros to the right of the 2 were measured or calculated out to be 0, or whether or not they are there to indicate the overall size of the number. So generally, when we are working with written numbers, we distinguish between the zeros that may or may not be placeholders and the other digits, which we refer to as significant figures for any given number. Significant figures are the known or measured digits in any number. If we look at the definition over here on the right-hand side of the screen, we can see that there are some rules that we can use to identify the significant figures in a given number. Non-zeros are always significant figures. So if I write down an example here, we have a 1 followed by 2 zeros. This has one non-zero digit, the 1, so this number has one significant figure. Zeros between non-zeros are also significant figures. So in another example, I might have the number 101, 101. In this case, there's a 0, but because it's sandwiched between two non-zero numbers, the 1s in this case, we know that this is a known or measured value rather than just a 0 that's being used as a placeholder. In this example, we have 3 significant figures. Finally, we have zeros to the right of non-zero digits if a decimal is indicated. This one's a little bit tricky, so bear with me. Once again, we have a number. Let's stick with the number 100, except this time I'm going to write it as 1, 0, 0, decimal 0, 100.0. In this case, because I voluntarily wrote the decimal place and wrote a 0 to the right of that decimal place, when it makes no difference to the size of the overall value, I'm actually trying to communicate something about the precision of the number in the way that I wrote it. By doing that extra writing, I'm communicating that those zeros to the right of the 1 are actually measured to be 0. They're not just placeholders telling me the magnitude of the number. Those numbers are known to be 0. This number isn't 100.1 or 99.9. This number is 100.0. The zeros to the right of the 1 are known values, and this means that they're significant figures. So in this example, we have 1, 2, 3, 4 significant figures. As a quick side note, this is also true even if I don't write a 0 to the right of the decimal place. If I wrote 100 followed by a decimal point, the zeros to the right of the number 1 would once again be considered significant figures. I'm indicating that by going through the extra effort of writing the decimal case. In this example, we would have 3 significant figures, the 1 and the 2 zeros. Now, if we apply this new information back to the 200 tons of fuel required for the Mars orbiter, we can see that we have a number 2, followed by 2 zeros, and no decimal point indicated. This value has one significant figure. We can only assume that the 2 is significant, and the zeros are probably just being used as placeholders to show that this number is in the hundreds rather than the single digits or the thousands, for example. Practically, we interpret this to mean that we don't know the exact value of the digit to the right of the 2, but whatever it is, it's fair to assume that the overall number rounds to 200. And for those of you that remember your rounding rules, you'll know that the true value of this number could be anywhere between 150 and 240, because if the value on the right of the number is a 5 or higher, you round up. And if the value to the right of the two is a 4 or lower, you round down. So 150 would round up to 200 if we were only expressing one significant figure. 240 rounds down to 200 if we are only expressing one significant figure. Here we can start to get a sense that the accuracy to which we understand numbers depends on the decimal place you are rounding to. Now, all of this can be a little frustrating and confusing at times because despite our use of the written decimal point, there is still some ambiguity about whether or not zeros are significant figures or placeholders. It's totally possible that when I write down this value of 200 tons, that I actually know two of the digits in that number. Maybe I actually calculated or measured the zero in the tens place, for example. In this case, this number would have two significant figures, but I would have no idea based on how this number is currently written. And if I explicitly wrote the decimal point, that would indicate that we now have three significant figures for certain, and that isn't the case. This is where our old friend scientific notation swoops in to save the day. The beauty of scientific notation is that it is a way of writing out numbers without placeholder zeros, so there's no ambiguity about the number of significant figures. For example, someone might provide you with the weight of the Mars orbiter written out in scientific notation. They might provide you with a number that looks something like 3.00 times 10 to the third pounds. In other words, 3,000 pounds in scientific notation. All the digits multiplying the order of magnitude are significant figures. So in this example, we have three significant figures, the 3 and the 2 zeros indicated after the decimal point. This provides a lot more information about the accuracy of this number than writing it out as a 3 followed by 3 zeros, which is what we call decimal notation. In decimal form, we don't know how many of the zeros are known digits, and we have to assume that they're placeholders unless we are given additional information. Scientific notation removes all of this ambiguity. Now, this means that we need to be careful to include all of the significant figures when we're writing values in scientific notation in order to communicate those values accurately. For example, imagine that I know the exact distance that the Mars orbiter is going to travel over its lifetime down to the single mile. It would kind of be a coincidence for it to travel exactly 485 million miles, but let's just go with it for the sake of this exercise. To express the distance of exactly 485 million miles down to the single mile, we would write this as 485 followed by 6 zeros, because a million corresponds to 10 raised to the 6th power, which adds 6 zeros to any number. And we follow it all with a decimal point if we're trying to express that all of these digits in the number are significant figures. All of these zeros are known values, not placeholders. Now, if we were to write this number in scientific notation, I'd have to include all of these digits because in scientific notation, we make sure to write down all of the significant figures in order to make them explicit. So I would write it down in scientific notation as 4.85 followed by 6 more zeros to the right of the decimal, which are all significant figures, and I would multiply that by the order of magnitude, which in this case is actually 10 raised to the 8, to get all of those 6 zeros to the right of the decimal place, as well as the 5 and the 8. Okay? This is one of the rare examples where scientific notation doesn't save us a lot of space on the page or ink in our pens, because we actually have to write out more information than we did if we were just writing it in decimal form. But most of the time, scientific notation does allow us to write numbers more compactly. And in this case, the example does a good job of highlighting how scientific notation tells us exactly how accurate our numbers are.